Hello, everyone. The vastness of our universe is truly mesmerizing, isn't it? It's incredible to contemplate just how immense it is. However, at the same time, this vastness can also be quite disheartening. Think about it, if we were to discover another Earth-like planet in a distant galaxy using our powerful telescopes today, one that could sustain human life, it would take us centuries to reach it. In fact, for individuals, leaving our own galaxy is currently impossible. As we know, our planet Earth resides in the Milky Way galaxy. The nearest galaxy to us is the Andromeda Galaxy, which is approximately 2.5 million light-years away. If we were to use a spacecraft to travel there at the average speed of 28,000 kilometers per hour, it would take a staggering 94.5 billion years to reach our destination. Even if we were somehow able to travel at the speed of light, it would still take 2.5 million years. It's undeniably disappointing to realize that, despite finding countless planets, the practicality of reaching them remains an insurmountable challenge. But what if there was a shortcut, a way to transcend the confines of our galaxy? Imagine being able to traverse millions of light-years in just a matter of months. This is where things start to get intriguing. And this is where wormholes come into the picture. Wormholes are the shortcuts I'm talking about, my friends. You may have heard of them in the 2014 film Interstellar, which happens to be one of my all-time favorite space movies. In the film, Cooper and his team leave Earth in search of habitable planets and journey to another galaxy through a wormhole. According to the story, this wormhole was discovered near Saturn's orbit by NASA and plays a pivotal role in the plot. Interestingly, wormholes aren't just a product of science fiction, they are based on real science. But what exactly are wormholes, and how can we utilize them? To understand this, we need to revisit Einstein's theory of relativity, which I briefly mentioned in my video on black holes. Let's delve a bit deeper this time. When Albert Einstein formulated his theory of relativity, he expressed it through a set of equations known as Einstein's field equations. These equations, comprising 10 nonlinear partial differential equations, were first publicly revealed on November 25, 1915, when Einstein submitted his paper to the Prussian Academy of Sciences in Berlin, Germany. Though these equations appear complex, they can be simplified into a single equation, like this one you see here. Don't worry, we won't be diving into the mathematical intricacies today, as it can become quite dizzying. Broadly speaking, these equations describe how matter and energy influence the curvature of space-time. Einstein compared this curvature to a mesh, where objects placed on it cause it to bend under their weight. Similarly, the gravitational force of celestial bodies curves space-time around them. The greater the gravitational force, the more pronounced the curvature. Interestingly, even Einstein himself couldn't fully solve his field equations. He managed to find an approximate solution for a specific case, but it was Carl Schwarzschild who, in 1916, became the first person to solve these equations. Schwarzschild calculated precisely how much space-time curves in the presence of a single massive object. It was his solution that shed light on the concept of singularity and paved the way for the theoretical understanding of black holes. Fast forward about 100 years, and we finally captured the first image of a black hole in 2019, confirming what had been theoretically proven decades earlier. So, in essence, black holes were one of the solutions too.